All right. So let's start today talking about some announcements. Homework 2 was posted last week. It is due Friday, September 18th, so in a couple of days at 11:59 p.m. Eastern on Gradescope. The second announcement is Studio 2 was also posted last week. Here you are partnering up with someone in your section and submitting one Gradescope submission per group of 2 members. If you have not created your own WebEx team space just meant for 2 people, I would recommend you to create a space under our class, not outside the class. Under our class, call it section X and then followed by whatever name you want to give yourselves. So what you will do is when you start working on Studio 2, whenever you want, you just need to coordinate with your partner. Earlier the better, right? So start working over there. You guys will be working as a group of 2. And then when you have questions or for checkoff, you would log out of your small space of 2 and jump to the section space where you have TAs and undergraduate student assistants helping you through questions or checkoff. So you have been using a section 1 or 2 or 3 space for checkoffs until now, but you are going to create a smaller space so that you can work independently and then go back to that space for questions or checkoff. Studio 2 is due next week, so September 23rd, a Wednesday. But it is, in my opinion, Studio 2, if you read through the document and work with your partner, and I have given you 2 ways of doing Studio 2. One is considerably simpler than the other, and I recommended that in the document. It should go pretty quickly. It's not going to be very time consuming. The only criteria is for you to read the document carefully, because there are a few details that I want you to pick up about. How do you initialize vectors? How do you, what is the purpose of anodes? So take a look at that. Next, I also have, what is this? Class 1, 2, 3, 4. So quiz 4 is already on Gradescope. You guys can do that. Hopefully some of you have already done that. You guys can do it after class today. There's a question online. Can we check off during TA's office hours? Yes, absolutely. You can check off during TA's office hours. So far, what I have noticed and what other TAs have noticed is that the office hours have not been effectively utilized. So try to, sure, yes, absolutely. You can use TA's office hours to do the check off. Okay. The earlier the better, right? Because you can start working on the other things. You can move ahead in class. So what is on the agenda today? We are going to be starting to talk about digital circuits. This is lecture 2 of our class. The goal will be to discuss how we can implement logic gates using MOS transistors. So let's throw out a few logic gates that you may have heard of so far. Well, the simplest ones, the basic gates. Give me some basic gates. This is what we discussed at the end of last class. Basic logic gates. And, okay, or, okay, not. Beautiful. And, or, and not. And then some other logic gates which don't quite belong to the basic gates category are Nand, which is the opposite of AND, NOR, which is the opposite of OR, exclusive OR, and exclusive NOR. And you derive exclusive OR and exclusive NOR gates using basic gates or NAND and NOR gates. So exclusive OR and exclusive NOR are actually not gates, logic gates that are by themselves. They are actually derived using basic gates or NAND and NOR gates. So our goal will be to essentially talk about how we can implement these 5 gates using MOS transistors: metal oxide semiconductor, field effect transistor, MOSFET transistors, right? How do you put out these logic gates? How do you connect these transistors in such a way that you actually implement an AND function or a NAND function or a NOT gate? We'll actually also do this. We'll actually also talk about a buffer. How do you implement a buffer using transistors? We'll also talk about that. Now, many of you, might have seen some transistors. Depending on your previous classes, you might have seen the use of transistors in the on or off state, like the extreme versions, when the transistor is in saturation region or cutoff region. That's what we are going to be worried about, right? Using the transistor in the extreme cases, when it is on or when it is off. We are not going to be talking about when the transistor is in the active region, when there is a transition from the cutoff to saturation. Let's start talking about some Boolean operations. Formally define what's a Boolean variable. Now, you guys have looked at arithmetic variables so far, where you use some letters and say, okay, this is a variable which represents height or weight or temperature, right? So you have associated a variable with some physical quantities. In the same way, you can associate a Boolean variable with certain type of quantities. For example, is this color black or white? 0 or 1, right? That could be a Boolean variable. Hot and cold, low and high, sit or don't sit. Anything that you can classify as true or false, you can associate a Boolean variable with that quantity. And then once you have these Boolean variables, you can represent the relationship between output Boolean variables and input Boolean variables using a Boolean equation or a logic expression. Now, if the logic expression is false, that essentially means it has the value of logic 0 or simply 0. And if the logic expression is true, it has a value of logic 1 or simply 1. So we are now going to be talking about zeros and ones, but note that these are actually logic 0 and logic 1 representing false and true conditions. So 0 does not mean, we'll talk more about these logic values and voltages associated with these logic levels in just a bit. Now, in terms of basic operations, we have 3 of them: AND, OR, and NOT. The first two, this is your truth table, right? So this is a truth table of a 2-input AND gate. Now, the first question is, do AND gates always have to be 2 input? The answer is no. You can have a 3-input AND gate, you can have a 4-input AND gate. And you can actually put more and more gates together to build 5-input and 6-input AND gates as well. But this is just going to show you what an AND function does. The AND function, if it is between 2 Boolean variables, we have one input Boolean variable or binary variable X. We have another binary variable input Y. And the output, let's call it Z. Z equals X and Y. That's your binary output variable. It is taking certain values depending on what X and Y are for that particular row. So when X and Y, if any one of them is false, the output is false, right? If any one of them is a 0, the output is a 0. So think of it and as both have to be true in order for my output to be true. Both have to be 1 in order for my output to be 1, which only happens in the last case here. Now, are we going to always write X and Y using words? Probably not. We are simply going to just say Z equals X and Y. The dot operator indicates logical AND operation. And in fact, we can also write it like that, XY. Just as you express multiplication in arithmetic. Let's move on. For OR, the condition is slightly simpler, but it's the same story, right? You can have a 2-input OR, you can have a 3-input OR, you can have a multiple input OR gate. The output will only be one, but the inputs can be several. There will be some limitations on the number of things you can connect to the input. It is actually called fan-in limitation. And we'll talk about that at the end of lecture 2. So there is a limitation, a physical limitation. But logically, you can have many inputs. So how do I write this? I need to write this as Z equals X or Y. The plus symbol for OR. This or this. So if any one of them is true, the output will be true. This is true, output is true. This is true, output is true. Well, both are true, the output will definitely be true. So I just need one of them to be true in order for my output to be true. One of them, that's it. In other words, if one of them is 1, I don't even need to look at the other. I know the output is going to be 1. For a NOT gate, you will only have one input, one output. X is your input binary variable. Not X, or let's just use the same Z, is your output binary variable. And you represent that by putting a bar over it or a prime sign over it. One of these ways is fine. I'm going to be using this notation, X and then bar over it. In the textbook, you may see X prime. Both are denoting inversion operation. One input, one output. When input is false, output is true. Input is true, output is false. Those are your 3 basic gates. Let's talk about, so we have already talked about their truth tables. Their Boolean equations also we have talked about, right? Z equals X complement, Z equals X and Y, Z equals X or Y. We have talked about that. Now their symbols. This is an inverter or a NOT gate, a triangle followed by the bubble. The bubble actually signifies inversion. So note that. Bubble signifies inversion. Or complement. Or flip, however you want to look at it. 0 becoming a 1, 1 becoming a 0, right? That's the bubble. So the triangle actually denotes the symbol of a buffer. And we'll talk about what a buffer is in just a bit. It doesn't change the value of the input. So 0 goes in, 0 comes out, 1 goes in, 1 comes out. But because of that bubble, that's actually the inversion. 1 or 1 should be 0. No. So here, 1 plus 1 is 2. 1 or 1 is 1. This is OR gate. That is a addition. So there is a difference between addition and logical OR operation. We are talking about logical OR operation right now. So there are 2 different things. And yes, one exclusive OR 1 is 0. But the symbol for that is not a plus. There is a circle around that plus. So that is exclusive OR. Boolean algebra is different from arithmetic algebra. Some of the rules might be the same, but you should assume that it is different in general. So when we write logic expressions with multiple ORs, multiple cases can be 1, resulting in a total of more than 1 as an output. Well, no. So here, when you're writing this, right? So for example, if you have a logic expression as z equals x and y or x complement, right? That means that z can be true if this guy is true or if this guy is true. If one of them is true, z will be 1. Only when both are false, z will be false. All right, now let's talk about the symbol of AND gate. AND gate symbol, can we use a, yes, you can absolutely use that symbol as well, but I would recommend the bar over the X, this way, just to be consistent with everybody in the class. Now, X and Y, the symbol is a big D, right? So you have a flat line and then you have a semicircle. That's your AND gate. This is a 2-input AND gate. When you have a 3-input AND gate, you will have something like that. It's not a triangle. It's a D, right? Like that. So X, Y. Well, let's use something else. X1, Y, X2, X3. So Z is what? X1 and X2 and X3. So only when all three of them are true, the output Z is true. All of them, this and this and this, all of them have to be true. For OR, the symbol is slightly different. There is a triangle, but so this is the triangle that you guys see, but there is also an arc at the front. So I draw it like that. Or so you can have x1, x2, x3, z equals x1 or x2 or x3. If any one of them is true, output is true. So we've talked about basic gates, their truth tables, their Boolean equations, and their symbols, the gate symbols. Now let's talk about a logic signal. Now the reason for how many inputs can we have into a gate? So your question has a pretty detailed answer. The number of inputs you can have to a gate is based on fan-in limit. And we are going to talk about that at the end of lecture 2. So all the way at the end, there is a fan-in limitation of an AND gate discussion, and I'll talk more about that when we get there. Let's come back to right here, logic signal. Now clearly, whenever you are going to quantize a signal, right, convert an analog signal to a discrete signal, you are going to have to associate a few bits with each level. Now, when you associate some bits with each level, what you're doing is you are quantizing each value using a real value. Now, what happens because of that? Well, the digital logic ignores that quantization error. If you have two discrete states, then I can use one bit to denote that, right? So if you have two discrete states, 0 and 1, then I can just use one bit to denote that. 0, it is the low state, 1, it is the high state. But if you have 2 raised to n different values, then you need n bits to denote that. So for example, let us just talk about an example here. So let us say that you have now I'm going to just sketch an arbitrary signal. Let's say I have something like this, right? Just some analog signal. And my x-axis is right now time. And this is some function s of time. Now, when you're trying to convert this signal into a digital signal, meaning I don't want amplitudes like 1.3, 1.5, 1.7. I want bits 000, 001. I want binary, a bit stream out of this. First thing that you are going to need to do is decide the number of levels. Number of levels in your analog to digital converter. So let us say we have 8 levels. What does that mean? That means that from top to bottom, the dynamic range of your signal is divided into 8 levels. So let me just put that out here. 1, 2, 3, 4, 5, 6, 7, 8. Right. So I've essentially divided my vertical range, the dynamic range of my signal, in using 8 different levels. And at each level, I can associate a value. It doesn't have to be this way. I'm just giving you an example. You can arbitrarily decide that. 8 levels, so I'm going to need 3 bits to denote each level. Now, once I do that, I'm going to take a look at each sample. Okay, I've got a sample. So let's suppose I have a sampling rate, right? So I'm going to use pink for that. And then I'm going to say, okay, because I'm converting a analog signal to a digital signal, I'm going to be essentially sampling this at some rate. So each sample, I'm going to denote that as a pink line. Now, once I do that, what I'm going to do is I'm going to look at the first sample. Where is my first sample? My first sample is right here. So instead of saying the value as an analog voltage may be 1.3, I'm going to refer to that value as 010. How about the next one? When I sample it, it is going to be here. What am I going to associate with that value? Zero, 1, absolutely right. The closest one, right? Next value, right here. What am I going to associate with that? 001 again. How about here? 010, yes. And I keep doing that, right? So I do it here and I do it here. Where is next? Pink is here. Pink is here. Pink is here. Pink is here. And pink is here, right? And then I'm going to say, all right, those values are going to be, so instead of sending the signal as an analog form, I'm essentially going to send the signal as first one 010, second one 001, next 001, next 010, next 100, next right here is a confusion, right? So what if over here you are right in the middle? When you are right in the middle, you flip a coin and you decide. You can go low or high because it is in the middle. There is no way for you to choose one or the other. So you can just flip a coin and decide that. Flip a coin is the answer to your question. I flipped a coin and I got 110. Next 111, and next 110, and next. You guys get the idea, right? So here what was crucial? No rounding. We are just associating the closest level to which we have assigned 3 bits, right? So when you are thinking about converting an analog signal to a digital signal, that's what goes on. Now clearly, when you decide 8 levels, you are going to use 3 bits for it. Now, if you want the accuracy of this analog to digital converter to increase, then you might want to have 16 levels, 32 levels, 64 levels, right? The more number of levels you have, the more bits you will need for each level. But what you gain is the precision of converting that analog to a digital signal. So that's what we are talking about. This whole process that we did was quantization. So that's what it means over here, quantizing it to a real value, right? All right, next. When you talk about low, you are essentially talking about algebraic lower voltages, and you are essentially referring to logic low. So when you hear me say low or false or a zero, I'm talking about logic low, logic zero level. And when I refer to high, I'm talking about a higher voltage. And I'll talk about the range in just a minute. And I'm talking about true, 1, high. I'm referring to a logic 1. So let's talk about the range of voltages. Because logic low doesn't mean 0 volts. It actually means any voltage between 0 and 1.5 volts. But it actually depends on the technology that we are going to be using. So for example, this one is for Cmos, complementary MOS. That's what we are going to be using to make our gates. So this is based on Cmos technology. TTL and others will have different ranges, but these are the ranges that we are going to use for logic low and logic high. So when you say low or logic 0, you're talking about a voltage range of 0 to a 1.5 volts range, right? So it's not 0, it's actually a small value, a small range of voltages. And when you talk about logic 1 or the high level, you're talking about 3.5 to 5 volts. What about in the middle? In the middle, you have an undefined logic level, meaning if you have a voltage like, for example, 2 volts, you will not be able to associate that with logic 0 or logic 1. That is undefined. You don't want to be in that territory where there is a confusion between whether it is logic 0 or logic 1, right? You want to classify that as a black or white. You don't want to be in that gray region, because that can give you incorrect results at the end, right? So you want to be in either a low voltage region or a high voltage region. You don't want to end up in the gray region in the middle, anywhere between 1.5 and 3.5 volts for any of these binary variables, which could be represented using a voltage. Now, let me ask you this. This is going to be this discussion that we are just going to have is going to be very helpful moving forward, because moving forward in a few minutes, you are going to see one of the most confusing topics for the first 2 or 3 weeks of class. So I want you guys to pay close attention to what we are going to talk about. Now, let us suppose that I give you 2 voltages, right? So I give you a voltage over here somewhere. This may be a 0 or a 0.1 or a 0.2 volts. And the other voltage that I'm going to give you is over here. Which one do you like the best? Which one would you rather have, the black or the red? Black, closer to 0. Oh, okay. So why red? So black is what I would have because it is very close to 0, ideal voltage. It is far away from the gray region where I don't want to be. So I want to be here. Yeah? I want to be as close to 0.0 volts as possible, because as I go above that, as I go close to 1.5, I have a weak 0. So here I have a strong logic 0. This is a weak logic 0. You guys see that? Because it is it's prone to error. It is prone to a little bit of noise in my system can push it into the undefined logic level, right? A little bit of noise. Nikhil, you are absolutely right. Yes. So I hope you guys see that. One is a strong 0, one is a weak 0, right? Similarly, let us draw two more boxes here. And my color choice should obviously give away the answer here. That's the point. Which one would you rather pick? Black or red? One is close to 5 volts, the other is close to 3.5 volts. Black again. You would pick black again because that is a strong, conclusive logic 1. This is a weak one because a little bit of noise can push it into the undefined region. So I hope you guys are comfortable with this discussion because soon we will be talking about noise margin. You guys see what we talked about. We said the weak logic levels can end up in the undefined logic level due to some noise, right? So we are going to be talking about noise margin. How much noise can it tolerate without going into the undefined logic level? So this discussion will be helpful later on as well. All right, let's move on. So noise margin, right? That's later in the lecture. So this discussion will lead to that. Now, let's talk about how Boolean operations are going to be implemented. We are going to need to talk about a transistor. And this can become very, very complex, but I'm going to try to simplify this with a discussion which is, say, a real world example, right? So I'm going to try to make it very, very, very simple, just so that you guys grasp this. And it should be pretty easy because we are either talking about the transistor in the on state or off state, cutoff or saturation. Right? We are not talking about the active region. So you have three things here. For a metal oxide semiconductor field effects transistor, you have three terminals. It's a 3-terminal device. What are the 3 terminals? There is a gate, there is a source, and there is a drain. 3 terminals. If you guys have seen bipolar junction transistors or BJTs, those 3 terminals for BJTs are also transistors and they're also 3-terminal devices. For them, it will be what? Emitter, base, collector. So those 3 are the names of those 3 terminals and I have mapped them. So gate terminal is going to function as the same as the base terminal for a BJT. This is just for reference. We are not going to be working with bipolar junction transistors. We are going to be working with metal oxide semiconductor field effect transistors. Now, a transistor is as simple as a switch only when we talk about the on and off state, the saturation and cutoff region. So when we talk about implementing logic gates using transistors, we are going to be using the switching aspect of the transistors. Connected or not connected, open or closed, on or off. That's it. Only 2 states. Now here you see a diagram of that switch. S denotes the source terminal. D denotes the drain terminal. So these are 2 of the 3 terminals on the MOS transistor. So where is the third one? Gate. Where is it? Gate terminal is actually represented using the voltage that you apply at the switch. So the way this MOS transistor functions as a switch is when your gate voltage with respect to the source is greater than some threshold voltage, then the switch is going to be connected like that. Let me put it in blue right here. It's going to be connected. Meaning, if your gate voltage with respect to the source terminal is greater than some threshold voltage, then the source terminal will be connected to the drain terminal. They both will be connected through some small resistance R sub on. If VGS, voltage at the gate terminal with respect to the source, is less than some threshold voltage, then source and drain terminals are disconnected. As simple as that. When the voltage at the gate is higher than a certain value, source and drain are connected. When the source voltage, gate voltage is not there, it's less than the threshold voltage, then the source and the drain are disconnected. That's it. Is that the internal resistance or some load? No, it's internal resistance. It is not a load. For the purposes of our discussion with respect to logic gates, we are going to assume that R on is 0. Now, how do you represent this scheme using the symbol of a transistor? Again, as you can see, I want you to draw parallels between the diagram on the left and the diagram on the right. On the left, you have a switch. On the right, you have a MOS transistor that we are going to be using. Source, where is source? Over here, pink. Over here, pink. That's your source terminal. Where is drain? On the right. And over here, that's your gate. So let me also use this for, yellow, gate. So when the gate voltage with respect to the source is high enough, then these two are connected. Or I can actually draw it like this, right? I can say if VGS is greater than or equal to VT, then here is your source, there's your drain. They are connected. On the other hand, if VGS is less than VT, then your source is disconnected from your drain. So this is one box, and that is the other box. Probably not. Those two statements. How do you determine that the threshold is determined already? Let me talk about that in just a second. It's already there. It's already determined for transistors. Let's see. So this is also called the on state for the transistor. On means source and drain are connected to each other, which is this. Off, the transistor is off. That means source and drain are disconnected, which is right here. So all you will be looking for is whether the gate voltage is high or low. You have two, right? High and low. There is your answer. If it is high, then it is greater than the threshold. If it is low, it is lower than the threshold. So you are going to be talking about logic 0 and logic 1. So if it is in the range of 0 to 1.5, it is working as a low voltage. If it is in the 3.5 to 5 volts, it's in the high voltage range. Let's move on. oh, sorry. Let me also give you like a real world example, right, of all of this happening. VGS means absolute value of VG minus VS. Yes, you got it. VG with respect to S. So it's a differential voltage. Yes. Let's talk about a room, right? So suppose there is a room over here. Let me put a diagram of a room here. And I will say this is my room. Oh, come on. And at some point I have a door. And there are people outside who want to enter the room. When can people enter the room? When the door is open. You got it. People cannot enter room when door is closed. Now I want you guys to match the following. On the left column I have three things: source, gate, drain. I want you guys to think about how you are going to match source, gate, drain to room, door, people. People is source, door is gate, room is drain. You got it. Yes. All right, let's color code them. Source, people. And you know the other one is, second one is very obvious, right? Gate, a door, like that's obvious. And then the drain is where everything collects inside the room. When the gate, so now you see it's the gate voltage that it is determining whether people can enter or not, whether the source and drain are connected or not. You guys see that? So it's going to be as simple as that, right? Because we are only talking about the door being closed or open. We are not talking about what happens as the door is opening or as the door is closing. We are not talking about the active region. We are talking about the two extreme cases. All right. Now the symbol of an NMOS transistor. So there are going to be two types of transistors. There's an N-channel metal oxide field effects transistor and there's a P-channel field effect transistor. So N-channel is called NMOS. So N-channel MOS. What does N-channel mean? N-channel means that this transistor was made by sandwiching a negatively doped semiconductor material between two positively doped semiconductor materials. So P and P, right? It's an N-channel transistor that way. What is the symbol going to be? The substrate is reference to ground, but the one on the right is what we are going to be using to sketch our logic gates and transistors in representing the logic gates. So the gate terminal is right here, the source is right here, the drain is right here. And we know how it operates, right? We know that the gate voltage, if it is with respect to the source, if it is high, then source and drain are connected, otherwise it is not connected. NPN is the other model? Yes, you got it. That is called Pmos, which is exactly the complementary of NMOS. So you see this table is going to be representative of the behavior of this transistor. So if gate voltage is 0, what does that mean? Gate voltage is 0. It just means that the gate VGS is less than VT. And that means it is off. The switch is off. In terms of our source and drain connections, source is here, drain is here. Disconnected. Let's do the other case. The other case is gate voltage is 1, meaning VGS is greater than or equal to VT. It is on. On meaning DS, connected. So it's going to be as simple as that. Either it is disconnected or it is connected. Now, some of you have already started talking about NPN. Yes, it is going to be Pmos. So P channel MOS. NPN, a positively doped material. It is sandwiched between two negatively doped materials. And I'm using gate voltage and I'm applying that to the positively doped material, and the two ends are negatively doped materials where I'm connecting the source and the drain voltage to. Now the construction of the transistors is not where this class is, right? That's circuits and IE. Right now we are simply using the transistor as a switch. So notice the difference. The difference was right here. The bubble. We know a bubble signifies inversion, and that's what it does. So for a Pmos, you will see bubbles in front of the gate terminal, but you still have gate, source, and drain, and it is exactly functioning as the same NPN transistor, except now everything is reversed. So when G is 0, you see this, when G is 0 here, that essentially means that you are applying a 1 at the gate, because that bubble signifies that. So let's talk about these two cases. G is 1. What does that mean? That means now with the complement, VGS is greater than or equal to VT, and it is on, meaning source, drain connected. Next case, VGS less than VT, off, source disconnected from drain. Exactly the opposite. So that's, what is VT? VDD is the supply voltage, and we are going to use VDD as, so when we start talking about how do you put this together, we are going to need two connections to be made. One is ground and the other is power supply. The power supply, or the voltage at the drain, is being represented by VDD, and it is usually going to be a voltage that is between 1 and 5 volts. For our purposes, we are going to work in the safest region, 5 volts. So think of that as the supply voltage. This is going to be your first. What does NPN stand for? NPN stands for how we make the transistor. We are making the transistor using 3 different semiconductor materials. One of them is positively doped, meaning more holes than electrons. That's in the middle. It is sandwiched between 2 negatively doped semiconductor materials at the sides, N and N. So NPN transistor, in our case, is a P-channel MOSFET or a Pmos. So we will be referring to that as Pmos. And the other one, which was PNP, that is NMOS. Let's talk about CMOS inverter. So what are we talking about? What does CMOS inverter mean? Meaning we are using the CMOS technology to establish those voltage ranges, and it is an inverter. So it's a NOT gate. It complements the input. It is going to be our first logic gate that we are going to implement, that we are actually going to make using two transistors. One of them is NMOS. Let me use blue for this. And the other is Pmos. So I need two transistors to make one inverter, one NOT gate. What did I do? I have connected these inverters or transistors in a particular manner. And only when I do that, complementary. You see, NMOS and PMOS, they are complementary to each other. So both combined, it's a CMOS circuit. So you have two transistors. What did you do? Let us talk about, actually, let's do this first. Let us identify their terminals first. Of course, this has to be gate. That is going to be my drain, and that is going to be my source connected to my supply voltage. VDD, assume 5 volts, as high as we can have. Next, this guy also needs 3 terminals. That is going to be my gate, that is going to be my source connected to ground, and this is going to be my drain. So I've identified the 3 terminals of both transistors, and just for the sake of clarity, what I'll do is I will name them Q1 and Q2. You use Q as the letter to identify transistors, just as you use R and C and L to identify resistors, capacitors, and inductors. You use Q for transistors. So you have Q1 and Q2 for NMOS transistor and PMOS transistor. There is an input here. The input terminal is connected to the gate terminal of both the transistors, right? Input voltage connected or controlling the gate terminal of both transistors. Where am I measuring the output? I'm measuring the output at the drain terminals. They are both connected for both the transistors. The drain terminals of the 2 transistors. That's where I'm measuring the output. Now this CL is simply a capacitor that is going to ground any high frequency noise that I may have, some digital noise. So for now, just ignore CL. Let us focus on whether we can establish a relationship between input and output. The claim is that one should be complementary of the other, because it's supposed to do an inversion, not gate, right? So I would like to do this. I would like to make a table here. I will have one column for input. I have one column for Q1. I will have another column for Q2, and I will have the last column for V out. What I'm going to be doing is I'm going to be monitoring the state of Q1 and Q2 as I fill out this table. The good news is that I only have 2 entries in this table. Remember, what is V in? V in is a voltage, but that voltage is indicating the state of a binary input variable. So let me call this in, and this is out. So in is an input binary variable to my NOT gate, and out is an output binary variable of my NOT gate. And the voltage that signifies that, I'm calling that V in and V out. So because it is a binary variable, I only need to talk about whether V in is in the low category or the high category. So let's start with low. When V in is low, what is the state of Q1 and Q2? Now I want you guys to think about on and off. That is Q1 and that is Q2. Q1 is off and Q2 is on. So Q1 is off is the right answer, right? Because Vin, if it is low, it is not enough to connect the source and drain. It is not enough. So those two connections are open circuit. In other words, Q1 is off. How about Q2? Well, Q1 and Q2 will always have to be complementary because of that bubble. And we have connected them to the same input voltage that's connecting the same, the gate of both those transistors. So if Q1 is off, Q2 will have to be on. Now, if Q2 is on, what does that mean? Now let us talk about this. Now let us talk about, you said Q1 is off. What does that mean? In blue, this is disconnected from this, right? And we said Q2 is on. What does that mean? The source here is connected to the drain there. What am I going to read at the output? V out is disconnected from ground. V out is directly connected to high. Plus 5 volts is what I'll read. Yes. You guys see that? Low, high. Inversion. Next, let us do the other case. What is the other case? Of course, it has to be high. When the input is high, let me erase these things here. There and then there. Okay. Now tell me what is the state of Q1 and Q2. Q1 is on or off. Q2 is on or off. It's going to be exactly the opposite, right? So Q1 is you guys are right. Q1 is going to be on. Q2 is going to be off. What does that mean over here? Disconnected and connected. What is V out going to read? 0 volts, low. When the input is high, the output is low. So you guys see how we have taken two transistors, Nmos and Pmos. We have connected them in a particular configuration to get an inverter, right? So how are we inverting the signal at Q2? We are not inverting the signal. It is actually constructed in a complementary manner. So the construction itself, NPN, right? With respect to here, Nmos, that was PNP. So the construction itself is complementary. But in terms of a symbol, we use a bubble to signify that inversion. Now, what I'm going to do is this. I will just draw my Cmos inverter. That's my Cmos inverter. This is my input and this is my output. Now, I'm going to ask you guys this question. V out can be plus 5 volts due to the presence of blank. And the other question is, V out can be 0 volts or low due to the presence of what? And I'm going to call them Q2 and Q1. Can we answer this question? Too much noise can give you error. No. So wait a second. Does this mean that the input voltage is 0? It is. So low means a voltage that is low enough, right? So 0 to 1.5 volts. So you guys have said Q2 and then Q1. So V out can be plus 5 volts due to the presence of Q2. And that's the right answer. And then the next one is V out can be 0 volts because of the presence of Q1. That is also the right answer. Right? Because that's what is connecting V out to plus 5, Q2. And Q1 is actually the one that is connecting it to low. So if Q2 was not present, then V out will not have the ability to go to plus 5, and the other way as well, right? So what I'm going to do is I'm going to call this guy pull up network. Now I hope that you see a connection between that question right there and the naming that I used for that. Pull up network. It is because of that network. In that network right now there is just one transistor. But due to that network, the pull up network, V out is able to be pulled up to 5 volts. And of course, the other one will be pull down network. Right. So I've asked these two questions over here just for you to identify what is pulling the output to 0, what is pulling the output to plus 5. If Q1 is not present, what will happen? So it's not as much as transistor not being present. I'm talking about what is that functioning as, right? What is it functioning as? What is C underscore L in the previous diagram? So that is a load capacitor. Load capacitor whose function can be to ground any high frequency noise that may happen at V out. So I hope you know capacitors are frequency sensitive, right? So the higher the frequency, so it's a noise fixer, yes. Digital noise fixer. So pull up network and pull down network, we have identified them. Now let me ask you another question. I still don't understand the idea of noise. Don't worry, we are going to spend a lot of time talking about noise margin. Noise is anything that is corrupting the value of your logic signal, right? So if the voltage is 0 volts and there is a noise of amplitude 0.1 volts, and if it is an additive noise, then the signal plus noise becomes 0 plus 0.1 becomes 0.1, right? So noise is something that is essentially corrupting the voltage that you ideally want them to have. Let's see. The next question is this. Are pull down network and pull up network complementary to each other? Yes. Pull down network and pull up network and pull down networks are complementary to each other. Something to note. Moving forward, we are going to need this. All right, let's move on here. Now, we have already done the analysis of that particular circuit using transistors. But if you wanted to do this analysis using a switch model, you could do that. For example, when V in is low, this was what? This was our Q1, this was our Q2, and then this was our Q1, this was our Q2. Pull down and pull up network respectively, right? So when V in is low, that switch was open, that switch was closed, and V out was reading high voltage. And in case B, when V in was high, Q2 was open, Q1 was closed, and V out was being pulled down to ground. V out was low in that case, right? So the switch model can help you maybe look at the essential part of our circuit if this is getting a little bit too much information, right? A switch model, and we can draw the switch model like for other things as well. Now we are going to expand on this, of course, because we are going to need to design and or not everything, right? So let's do this. Before we go there, let me ask you something else. Let me do buffer. A buffer is something that takes in 0 and gives you 0. It takes in a 1 and it gives you a 1 at the output. It doesn't change anything. So the question is, how should I implement this using transistors? Oh, no, we can't do that. No. We can't do that because of how the transistors are constructed. This is how we do it. A buffer is equivalent to a NOT gate followed by another NOT gate. So 0 goes in, 1 comes out, 0 comes out. 1 goes in, 0 comes out, 1 comes out. So a buffer is actually 2 cascaded NOT gates. So now let's talk about this. How do you do this with respect to this? I'm simply going to pick this out. I'm going to go back here. I'm going to paste one guy here, and then I'm going to paste another guy right here. And then I'm going to erase things that I don't need. And magic trick. That's it. You guys see that? So this became my intermediate. So let me call this Q3 and Q4. That is how you make a buffer. And the whole reason to use a buffer is because if you have a weak 0 here, you get a strong 0 output. And if you have a weak 1 here, you get a strong 1. You guys remember the weak and the strong logic levels from here? So it's just doing the same thing. It is solidifying, it is regenerating the logic level. making a weak 1 to a strong 1, making a weak 0 into a strong 0. Why is this necessary? It is necessary because when you have multiple things connected with each other, because of voltage division perhaps, voltages get divided, voltages reduce, and it may go from a high to accidentally in the undefined region when you connect multiple things together. To avoid those situations, you use a buffer. All right, so how many transistors do I need to synthesize, to implement a buffer? I need 2 NMOS transistors and 2 PMOS transistors to make a, I need 4 in total, right? So I need 2 NMOS. Those are going to be my pull down network. That's over here and here. So Q1 and Q3. And then 2 Pmos in the pull up network, Q2, Q4. Right. So I've got a total of 4 transistors, 2 of them NMOS, 2 of them PMOS, and that's how I get a buffer. Now let's talk about this. This is a CMOS NAND gate. NAND means what? NAND is exactly the opposite of AND. Now to get this, I have, what is in my pull down network? Can you guys tell me which transistors are in the pull down network over here? Q1 and Q3 are in the pull down network. Beautiful. And what about the pull up network? Q2 and Q4. Yes. Q2 and Q4 are in my pull up network. Now, the second thing I want you to notice is this. In the pull down network, we also said this, right? We also said pull up network and pull down network are always going to be complementary to each other, right? So what is the complement of series? Series, parallel, parallel, series. I got 2 transistors in series for pull down network. My pull up network has 2 PMOS transistors in parallel. You guys see that? They are all sharing the same gate voltages. A is connected to Q1, is also connected to Q2. B is connected to Q3, is also connected to Q4. So those are the first few things I want you to notice. Pull down network, pull up network, transistors in series, transistors in parallel, right? Now, I'm going to say a statement here. The only way Z can be ground, Z can be low, is when Q1 and Q3 are on. True or false? True. That's absolutely true. Because these 2 transistors are in series, they both have to be on. They both have to be connected. The source and drain terminals of both of them have to be connected. Only then Z can be ground. All the other possibilities, Z will be connected to the high voltage. So A and B need to be on. Yes, you got it. Yes, A and B both need to be on in order for Z to read ground. Where is that? It's the last entry in the table. A is high, B is high, Q1 is on, Q3 is on. And because Q2 is complementary to Q1 and Q4 is complementary to Q3, they are both off in that case. And Z is low. That's the only time. For all the other times, Z is on. Z is going to be high because it is going to be connected to VDD either through Q2 or through Q4 or both, right? Only one of them, Q2 or Q4, only one of them needs to be on in order for Z to be high. So if one is in series, the other must be in parallel. In terms of the whole network, pull down network and pull up network, yes. If pull down network has transistors in series, pull up network will have transistors in parallel. Your pull down network will have transistors of type NMOS. Your pull up network will have transistors of type PMOS. Now let's quickly go through this as well. When A and B are low, Q1 and Q3 are going to be off. Q2, so I hope you also see that Q1 and Q2 are going to be opposites of each other. And Q3 and Q4 are going to be opposites of each other. Because A, the gate voltage controls Q1, the same gate voltage controls Q2. And the same thing with respect to Q3 and Q4. So, low, low, Q1 is off, Q3 is off, Q2 is on, Q4 is on, and you see Q2 is on, Q4 is on. That means that Z is connected to plus 5 volts using two parallel connections, but it is connected to high, so Z is going to be high. For the second case, it is going to be connected to high using Q2. For the third case, it is going to be connected to high using Q4. Both, let me use blue here, both, one of them. And only in the last case, when both A and B are high, only then Z will read 0 volts. Otherwise, it will read high volts. Now, you see, this is exactly the opposite of AND, right? So, you see, 0, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1. You see that? So, your truth table.
Truth tables? Oh my god. Have you taken linear algebra?
I took multi. I wanted to take linear, but it got full. So.
You guys, the multivariable calculus is a very interesting discussion, but I can hear you guys.
Okay.
So let's see, A and B. So what do you have? For A and B, you had 0, 0, 0, 1. What do you have here? 1, 1, 1, 0. Exactly the opposite. So let me write it clearly. Exactly the opposite of AND. A bar over it. The symbol AND followed by a bubble. Or you could also say AND by that, right? Followed by the NOT gate. A, B, A and B, A NAND B. Now, so how do you make, so the last thing is this, the last thing I want to talk about is how do you make AND gate? That's where we'll stop. How to make AND. So we know how to make NAND. How do you make AND? You do this. A, B, you got A NAND B, and then you invert that. Double inversions cancels out. So in terms of a circuit, what are you going to have? You are going to have this guy But this point, you are going to connect to this a NOT gate. So let me take a NOT gate here. Paste it right there. That is going to be your. I didn't do a good job here, but you see. I hope you see how do you make that, right? You first design a NAND and then you put a NOT gate in front of it. CMOS NAND followed by a CMOS inverter. That's how you get to an AND gate. How many transistors do I need to do this? How many transistors do I need to do this? Six is absolutely right. This guy needs 4. This guy needs 2. Half of them will be in the pull down network. Half of them will be in the pull up network. Let me ask you this. How many transistors do I need to synthesize a 3-input AND gate? That was a 2-input, right? What about the 3-input? 6 cannot be right because 6 is 2-input AND gate. 8 is right. And the reason is 8 is correct is because of this. You will have 3 transistors in series here. You will have 3 transistors, Pmos transistors in parallel here. So 3 plus 3 will give you 6. And then you, of course, will add the 2 from the NOT gate. You will have 8. So that is going to be 1, 2, 3 and NAND and then NOT. So this guy will need 6 and then this guy will need 2. All right, let me stop recording here.